Hey everybody, welcome back to part B of the running averages video. If you recall from the previous video, we were looking at a running average estimator in a situation where we have a resistor which is not changing with time, and so it's a static resistance, and we're just computing the running average. The truth is shown in blue there. The measurements are the red dots. It's basically the truth plus the measurement noise on top of that. And then the estimator is just averaging all the data points that we have. So we start with one data point and then go all the way to 50 data points. And you can see that the running average eventually gets pretty close to the truth. But there are some shortcomings. It uses all the data points, even those from the remote past. The gain gets smaller and smaller, so the running average filter goes to sleep and becomes insensitive to new measurement information. So we might want to try to improve things with a simple moving average. What's a simple moving average? A simple moving average of window size M only averages the M most recent measurements. So it's a sliding window that's moving right along, throws out the oldest measurement and incorporates the latest measurement and then moves that window along. Otherwise, it keeps everything within the window. And it's just averaging those M data points at any point in time. And it's got a fixed gain of 1 over M because it's only averaging M points. And of course, that never goes to 0. So suppose you have N data points. Your number of samples is N, which is greater than M. Then your moving average mathematically is just at any point in time, K is sum of the average of the last M data points, including the current one at K. Now, you can formulate the running average so that it's a special case of the moving average, if you will, and you can also define the moving average so that until you get at least M data points, the moving average will be equal to the running average. So that if your window size is the same as your number of samples, it's essentially just a running average. So here's the recursive formula, which makes sense. It's the old average plus 1 over M times the difference between the latest measurement and the oldest measurement. So as the window is moving forward from the previous time K minus 1 to the current time K, you're going to lose your oldest measurement that you had before, zk minus m plus 1, so you want to throw that away. But you're acquiring a new data point, zk, so you're adding that in. Otherwise, all the other data points in the window are the same between k and k minus 1. So intuitively, this formula makes sense. So here's how the simple moving average estimator with a window size of 10 performs on a static resistor problem. You can see it's still kind of bouncing around and chasing the noise. If there's a predominance of measurements on one side or the other of the truth, it's going to chase those. And it depends what's falling in the window of here size 10. So it has some shortcomings of its own. It's somewhat overly conservative about updating the previous SMA value. However, this is because the unchanging process dynamics means that the measurements don't change much. So it does well on dynamic situation where it is changing, but it's slow to change. That's part of the problem. More aggressive formulation of the recursive SMA could be done with, say, an exponential weighting scheme where you don't weight all the measurements the same. Neither of these averaging filters, however, takes into account the explicit uncertainty that you have in the process dynamics. So the process may have some noise built into it, independent of measurement, just because your mathematical model is not perfect. And also because there may be some random forcing functions or disturbances that are driving your process. Ones that cannot be characterized in any systematic way. It's just noise, white noise. But if you know what the uncertainty is associated with that white noise, that would have an effect on the uncertainty in your filter and how you weight things. And that's something that we'll see ultimately when we get to the real Kalman filter. So here's a simple moving average estimator with a dynamic problem. This is not very realistic, but let's pretend for the moment that the resistance can change with time. And then we're taking continuous measurements, and it's changing in a sinusoidal pattern. Then the truth would be this blue sine wave. The measurements, again, are bouncing around the sine wave. It's just the sine wave plus noise. And then we have our estimates from the moving average estimator. You can see that the moving average estimator tends to lag behind the sine wave. It's picking up the frequency okay, but there's a bit of a lag. Now, changing the window size to something even smaller will kind of reduce that lag. It's going to respond a little faster to what the sine wave is doing, but there's also still some overshoot and undershoot. Finally, if we take a look at the running average estimator, which is a simple moving average, but with the window size being the same as the number of samples. So the view graph is incorrect. The size is not 50. The size is not 5. It's 50. But what happens here on the running average is, at first it's kind of following the sinusoidal pattern, but as you get more and more data points, because it's using all the past data points in the average, it's going to smooth out over the long run, and you're going to basically get a straight line in the end around the center of the sine wave. Okay, so now we're going to switch over to our Python script. What you see here is the Spider IDE that Anaconda provides. This is the program that I was just showing there before. It's called DIN Simple Moving Average Demo. It generates the plots that we were looking at. I've got two possible models here, a dynamic model and a static model. Right now I've got the static model selected. We'll run that and we'll get the plots here in a second. Let me step through the program just a little bit so you can see how we do this. So to get our truth, we're starting with an initial truth value, and then generate the time samples, if you will, the 50 time points in this case. That's the number of samples. And then to get a static vector of values, we just take that single truth value, multiply it by an array of all ones from NumPy. For the estimation, we start with an array of zeros, and then we generate a random normal sequence with a mean mu of 0 and a sigma of 0.5. Add those to the truth vector, and that gives us our measurement vector. For the moving average, we need a window size, so set it, say, initially to 10. Calculate the gain, it's 1 over W. And then we call the function SMA to get our estimator. Now let's take a look in this other buffer here at our estimator. Our estimator function is right here. Takes in a data array and the window size, calculates the gain, and then it looks at the whole range of indices, and then if the index is smaller than the window size, it means we don't have a full window yet of data to do the moving average with, but we can do a simple average, and that's just the mean here. So that's why in the first branch here I'm taking the mean of that data, whatever data we have so far. And then once we get an index that's greater than the buffer size, then we apply a recursive formula for the computing the SMA. And that's all there is to it. And that's and setting it up like this is you can see why if the window size is at least as great as the number of data points, you'll never get a sliding window. You'll just have one window, and the result will be the mean of all those. So that's the running average. Okay, and just a quick note on this utility function that I have down below, the TME plot. TME stands for truth, measurement, and estimate. So we're going to see a lot of these plots here where I plot those three things. I'm going to use the same styles and the same approach, same colors and so forth. So I just made a function that will do that. And then down here, depending on how many samples we're dealing with, we can determine whether it's a simple moving or a running average. Get some labels for the axes and the title for the whatever the plot is. There's 5 plots. Let me just run this so you can see what happens. Okay, so in the beginning, I just plot the truth itself and then add the measurement noise so you get measurements. And then the estimator is run. And then I change the window size. This is a simple moving average. And then change the window size to 5. And then the recursive average, which is done by the recursive running average, which is done by setting the window size to the number of samples. So that's all there is to this Python script. So going back to our slides, let's see where we're at. So we've looked at the Python implementations of the running average and simple moving average. We've run some simulations of both constant and dynamic scalar processes to see how the different averages perform. What's coming in the next video? Next video, we're going to take a look at the prediction part of the Kalman algorithm, where we have real dynamics, so there is some real prediction computation that has to be done. All right, so that does it for this video. Thank you very much. We'll see you in the next.